you can already see that there is a large degeneracy. I can change this value to get the second peak to rise up. I can decrease this, and so on and so forth. So what is it that we're supposed to do? This schematic here essentially gives an idea of how the microwave background spectrum changes with variations of the various parameters. So the simple thing to do, the first approach to get a handle has been to adopt a minimal model. The minimal model has essentially 6 parameters. We have the baryon density, we have the dark matter density, we have a characteristic scale having to do with when the photons and the baryons are released from each other. And some of the parameters, like the dark energy equation of state, is fixed to a value of -1, which means that the assumption here is that the dark energy is behaving like the cosmological constant that Einstein introduced in the equations at an early epoch, that the sum of the neutrino masses is taken to be equal to the lower bound of 0.06 eV. The number of neutrinos is fixed at 3. And so with these kinds of assumptions, constraining some of the parameters and then allowing a small set of parameters to run wild, we can try and figure out and get a better constraint. We do get better constraints. We can get down to 10% uncertainties, 5% uncertainties, but there's still a lot of degeneracy in the parameters. And this graph, this visualization essentially attempts to show that. You can see that if I run along the x-axis here, I can change values in the y-axis, but it's not just the degeneracy in any 2 parameters. This plot actually shows you that there is a degeneracy in 3 parameters, and in principle there are degeneracies that are at higher dimensional than that. The 3rd dimensional is a Hubble parameter, so you can see the colors are changing as I run across the locus of points. So how do we get better? If we want to move towards a percent level uncertainty or sub-percent level uncertainty, how do we do better than this? But before I even answer that question, the question is, why would we want to move to a percent level? What is the gain? If we already know the parameters, we know the age of the universe to 10%, does it make any practical difference? Well, it does, because as I just mentioned, to get to this stage, we had to make some assumptions about the nature of dark energy. But we would like to actually understand what the nature of dark energy is. Is it really cosmological constant, or does it behave differently? Is it a fixed number that's been invariant over the age of the universe, or does it change with time? To be able to answer questions like that, the parameters that are 0th order have to be constrained down to 1%, and preferably even down to less than 1%. In fact, experiments like Euclid in Europe and the LSST here, which Brown is part of, are essentially geared towards doing just this. So how do you get there? How do you actually start to reduce these uncertainties? Fortunately, we have complementary probes that can also test the large-scale structure of space-time in the universe and its expansion rate and other properties of that ilk. And these probes, amongst them are clusters of galaxies, which I will be describing today. Clusters of galaxies, as I mentioned, are the largest gravitationally bound systems in the universe. As a result of being the largest, or by virtue of being the largest, they are also the youngest. They are the most recently formed. So in some sense, we are actually observing, in a cosmologist sense, the evolution of structure, the very front edge of structure formation happening. And so by measuring the properties of clusters, the number densities, how rapidly they're changing over time, these features, these properties, allow us to then walk back and constrain some of the parameters like the extension of the universe. There's another advantage to using objects like clusters of galaxies. The CMB is actually giving us information about the universe at the last scattering, at high redshift, whereas clusters of galaxies actually measure the state of the universe at low redshift. So we have a lever arm from 380,000 years after the Big Bang to 13.7 years after the Big Bang. And so we can test evolution of some of these parameters by doing this kind of studies. I've already mentioned other probes. Supernova are examples of probes that we can use to study the properties of the universe. And this graph, this plot basically quickly gives an idea of what some of the other probes are. We have baryon acoustic oscillations, which is essentially looking at the epoch when the photons and the baryon fluids separate from each other. And when they do, the power spectrum of the large-scale distribution of baryons shows a little glitch in it. And one of the aims of experiments that try and study galaxy distributions over old sky and to large depths is to study where this glitch is happening at different epochs. The glitch acts like a standard ruler. And so by having a standard rural measurement at different ages in the universe, we can actually figure out how rapidly the universe is expanding. Weak lensing is part of the next study that is also studying the large-scale structure of the universe, but is also related to this measurement of clusters of galaxies that I will describe in a second. The idea being here that these curves are often running at different directions with each other. They have a different degree of degeneracy with refer to each other. And so by looking at, I'm not sure why that's happening. By looking at the intersection between these parameters, we can basically constrain and tighten up the uncertainties associated with these parameters. So I've been talking about using clusters of galaxies. Let me now turn to the next sort of topic, a subtopic, and answer the question, why clusters of galaxies? I've already hinted at the fact that clusters of galaxies are the youngest, the largest of the objects in the universe, and this actually endows them with sensitivity towards the expansion of the universe that we can exploit. This is probably the only slide that actually brings in what I do as for a living for 80% of my time. It's a numerical simulation of structure formation in the universe. You see that at an early epoch, the mass density distribution is rather smooth, but there are tiny little ripples embedded in that have presumably come out of inflation. And as gravity works its magic, ripples, regions that have slight overdensity of matter tend to draw in more matter due to extra gravity in that, in that region. And as gravity brings in more matter, the regions themselves become more established. They grow. They virialize in the sense that the systems themselves decouple from the Hubble expansion and become entities in their own right. What you're seeing on this side is actually a more zoomed in version of what would be happening at one of these yellow dots in the rotating cube. So what's happening here is you're seeing structure formation in a zoomed in sense. There is filaments forming. There are small structures forming along the filaments. By the way, those small structures are actually galaxy scale systems. They turn into group scale systems, which are sort of intermediate and low mass clusters, and then eventually everything piles into a bound system, which is gigantic from a mass perspective. But just to give you an idea, there are, a typical cluster has on the average of about 1,000 galaxies that usually are bigger than the Milky Way, whizzing about in these massive potential wells. And there's also a huge amount of dark matter, as well as a lot of baryons that are left over, have not formed stars, have been shock heated, are extremely hot, and radiate copiously in X-rays. So these objects are amongst the brightest X-ray sources in the universe. They are massive, and they have about 1,000 galaxies whizzing around at a velocity dispersion of about The rules for starting the simulation is basically, we know, well, our particle physics friends have given us inflation, power spectrum coming out of inflation. The power spectrum coming out of inflation has been processed through the epochs of the universe until the epoch of last scattering, for example. or even later than that because we can get away with it. So there's a transfer function that introduces curvatures in the power spectrum. Once we have a power spectrum that has taken into account waves, modes that went out of the horizon, came back into the horizon, we have a shape. You set down ripples in a dark matter distribution. So you have matter distribution, you set down ripples in accordance with the power spectrum. They're Gaussian random, so it's very easy to set up. And then gravity does its magic. So really, the processes that are being, in this particular simulation, the only process being modeled is basically gravity. And same with this one, although there is gas in this one, I'm not showing you the counterpart where you can actually see gas zooming in, getting shock heated. So what happens here is that dark matter is the dominant mass quantity. So initially, as a result of gravity, it's the dark matter that's being moved and builds up potential wells and draws in more matter. Baryons are coming along for the ride. But when baryons interact with other baryons, they shock. And so the kinetic energy is converted into thermal energy, and you get hot gas building up at that point. In the smallest systems, hot gas very rapidly cools through everything from Bremsstrahlung through metal cooling and ends up forming stars. So at the bottom of the potential well, you start building up stars, which is our galaxy.
So is it easy to understand why you only have one-dimensional structure filaments, but you don't have planes?
We actually do have planes. The way it starts out, we call them walls, but yes, basically it is. Things start forming wall-like structures first. The wall-like structures fragment into filamentary structures, and then at the intersections of filaments where there's concentration of matter, their shear fields are also converging streams of matter there. That's where you start seeing bound structures starting to form. And there's a hierarchy of filaments as well. So early on, there's very thin, small filaments, and you get small galaxies. Then filaments grow, structure grows. The kind of structure you're seeing there where the filaments are huge, and they're drawing matter in, they're funneling matter into a cluster of galaxies. So in this image, you can actually see the hierarchy of filaments as they collapse into a bigger and bigger filament. And a similar thing happens with the voids. I showed you in that picture of large-scale structure that there were empty regions. You can see in here that as matter gets drawn out into the filaments and into the planes, into these walls, there are regions that are essentially devoid of matter. And they're also devoid of galaxies, and therefore we have these bubbles, these large cavities, empty regions in the space. Now, if I looked at the mass distribution of clusters at different epochs, and I looked at how rapidly this mass distribution was changing, so I'm looking at the shape of the mass distribution, and I'm looking at how rapidly it evolves, it turns out that those two quantities are very sensitive to certain parameter space, so certain parameters that define the expansion rate of the universe and also the amount of matter in the universe and also the amplitude of the initial fluctuation. So that's one thing that we don't get from particle physics. Colleagues of ours, we actually have to somehow either empirically constrain it, and microwave background and structures like clusters of galaxies play an important role in determining what the initial amplitudes were. But the main thing that I want to highlight here is I have shown on this plot 1, 2, 3, 4, 5 cosmological models. The details of these cosmological models are actually not important. The lambda CDM is the conventional model that we work with today, which is 70% dark energy, about 20%, 23% dark matter, and the rest in ordinary baryons. And you can see that that is shown here in solid curves. It has a particular shape both at the low mass end and at the high mass end. How rapidly it truncates is important, and how rapidly it's changing as a function of time is important. The other model is the one I talked about earlier, that when I was a graduate student, this was the theorist's favorite model. It's the standard cold dark matter model where it's a flat universe, but most of the energy density in the universe is in the form of dark matter. And you can see that that has a slightly different shape, changes with time somewhat differently, and has a different normalization. There are more clusters of low mass in that particular universe. And similarly, if you look at different variations of the universe, you find that either the shapes are the same or they evolve somewhat differently. And the challenge here basically is to try and construct distributions of clusters of galaxies at different epochs in the universe and look at exactly how these curves are evolving and what their shapes are. The main problem with trying to do this, as you can see here, the distribution is a function of mass. That's a fundamental quantity, but we can't observe mass directly. We can observe light. We can observe clusters in X-rays. We can measure their X-ray luminosity. We can measure the temperature of the hot gas. We can measure the luminosity of all the galaxies that live in clusters of galaxies. We can measure inverse Compton effect due to the hot gas that's in clusters of galaxies, but these are observables. Mass is not a directly observable quantity. Now, I'm going to skip over this. It's a plot that essentially illustrates the argument that I made before. It's just showing two different models. Again, the standard CDM and an open universe. Again, showing that the shape and the evolution can make a difference. This one is, again, illustrating the same point, but I'll just take a moment to just point to the fact that here, the dark matter content in these curves has been held the same. The cosmological constant, so this is geometrically flat universe. Curvature is flat here. And in this instance, the dark energy content has been set to 0, so this is an open universe. But the dark matter content is identical. And you can see that there is a difference in evolution. The curves are not evolving in the same way as a function of time. The points there are data. And so in this case, it's pretty obvious that the open universe doesn't actually work in the sense that it doesn't account for the observed number of clusters and how fast they're growing in time. The problem is, how do we measure mass? And fortunately, nature has actually given us a way. This is an image of a galaxy, a cluster of galaxies, Abell 520. This is an optical image from combining CFHT, Canada, France, Hawaii, ground-based telescope data, and HST data. Now, I can tell you that in this case, it's sort of obvious that there is a cluster here. Maybe there's something here. The fact that these are clusters, this is one unified cluster, I'm quite willing to admit that as a theorist looking at this picture, I wouldn't have known that there was a single unified cluster here. I'm quite amazed when my observer colleagues will look at an image where, to me, it just looks like a random scramble of galaxies, and they say, a cluster of galaxies. This is the distribution of mass in that cluster of galaxies, and this is what we're after. And the question is, how did we do this? How do we get to the mass distribution, and how can we measure that mass? Well, clusters of galaxies are massive. And if you look at the propagation of light of galaxies that are much further away, so in the background, and you look at what happens to the light from these galaxies as they propagate towards us, that light passes through these potential wells, and they bend, so you can have multiple images. They shear. So if you think of a circular beam, a bundle of light rays that is sort of circular in shape, as it propagates in a region with strong gravitational shear, it will essentially change shape. It will become more elliptical. And we see these ellipses, elliptical shapes, distortions forming. For example, if you look at this image, you will see a swirling like pattern in blue galaxies. So the blue objects here that seem to be stretched out into arc-like shapes are distant galaxies. In this instance, I've zoomed into the center of the galaxy where the gravity is the strongest and shear is the most strongest. And that effect of strong shear is to actually distort the galaxies in a very dramatic fashion. You're starting to see features, an arc like this, if we had caught it at the right angle or right position, could just as easily have gone around most of that cluster, and that would be getting very close to Einstein's rings. So certainly relativity predicted it, but Newtonian mechanics can also get you the answer within a factor of 2. But to understand shear, you really have to at least work with some level of relativity. But the main point is that you're seeing a whole host of background galaxies that are being coherently sheared. And the more important galaxies are not these brilliant arcs that stand out, which we would refer to as strong gravitational lensing, but it's the hundreds of very small galaxies, like the blue one here, the blue one there. If you look around, you'll see even the smallest blue galaxies are stretched in the tangential direction. And the idea here is to measure the shapes of these galaxies and use the shape distribution and their orientations to get a measure of the shear, and then turn the shear into gravitational potential and then into mass. So this animation essentially illustrates what I am trying to describe. There's a cluster of galaxy growing. The light rays are bending, and as light rays bend, there will be shearing happening here, but there's also multiple images that could form. Again, multiple images, very strong arcs. Those are structures that are known as strong gravitational lensing. They are relatively few in number and restricted to a small region at the core of the clusters. We're actually interested in measuring masses out to large distances away from the center. And so we rely on the weak gravitational lensing, and then statistics becomes an important part of the game. This is another way of looking at that. There's a cluster of galaxies. If you focus on the front screen, then those are background galaxies. The light from these background galaxies is being lensed by the cluster of galaxies. You get coherent shear here. It doesn't look very coherent because there's also a projection of the galaxies in the clusters that are also visible in our images. And part of the challenge is to decouple the foreground galaxies, which do not get affected by gravitational lensing, from the galaxies in the clusters, which are of course not affected by gravitational lensing, and the background galaxies. You can see that the same image on this side, where if the galaxies are in the foreground, they basically get projected more or less as they are seen in the sky. It's a direct projection. So we are trying to look for these minute but systematic, coherent shear features. To do this, my collaborators and I got involved in an observational project. We have named this project the Canadian Cluster Comparison Project. It's, the acronym is CCCP, and our slogan is, "It's good for the masses." Now, if you laughed, you've just given away your age. Because I've tried this at conferences where there are younger folks in the audience, more younger folks in the audience, and dead silence. Nobody picks up on this. Anyways, the upshot here is that we basically selected 50 clusters. We actually went ahead and picked our clusters in a rather unconventional way, an unorthodox way, because the normal approach is to pick the brightest X-ray clusters, which we figured might be biased in some way. And besides, I got involved because there's this other half of this project that I was interested in, which is understanding the physics of gas in these objects. And so I had no interest in biasing myself to a very specific class of clusters. But it turned out to be a good thing at the end. In any case, Henk Hoekstra was a colleague of mine at Victoria, who's now moved to Leiden. He is one of the world's foremost experts on gravitational lensing. And so he, of course, suggested that since we are compiling this catalog of clusters, we have X-ray data, we have Sunyaev-Zeldovich or inverse Compton effect data, we have radio data. Why don't we just go ahead and apply for time on the Canada-France-Hawaii telescope and get very deep images of these clusters and try and do the weak lensing measurement. And so this is a very quick broad brush sweep idea of what it is that we're trying to do. We have galaxies. We're trying to separate foreground from background galaxies. Once we have background galaxies, we measure their shapes. The shapes can be directly related to the shear effect of the gravitational field. From the shear, we can measure the potential. There is, in these particular equations, there's an assumption being made that clusters of galaxies can be treated as if they are two-dimensional objects in a plane. But that's perfectly valid because the path length of light that we're dealing with is much, much, much bigger than the size of the clusters. And so this is basically, we're doing a simple optics calculation. And it turns out that if you do the full-blown calculation by integrating along the path, curving path of light, the results really do not change in any way, shape, or sense at the level we can measure it today. So this is perfectly sensible. This is an image that's showing you the orientation of the galaxies in response to the shear field of the gravitational field. And we can take the shear and basically turn it into, as I said, into potential. And the potential can directly go into a surface density. And the surface density can then be converted into mass, and we get a mass measurement. Measuring shear is theoretically simple. Trying to do it in practice is an extremely challenging proposition. Why? Because what we want to start with, as you can imagine, imagine that you have a galaxies that are perfectly circular. Well, if they get lensed, then you have a shear, you have a coherent shear here, that's all great, you can measure it. But the true background galaxies have shapes that are already have elliptical-like shapes, and they are randomly oriented in some sense. And if you want to understand how the transition, how shear has damaged or impacted the shapes of these clusters, you have to have some idea of what the original distribution was. That's one aspect. Then, as I mentioned, there is the foreground and background objects that of course, wash out the signal because foreground objects are not getting lensed. The galaxies themselves are very, very faint. We're looking at galaxies that are in the background. They're very far away. They're very faint. As they get fainter and fainter, the noise in the CCDs themselves, the sky noise, the CCD noise itself, starts to make a difference. Atmosphere, what a nuisance. That twinkle that everybody has romanticized is the most irritating thing there is. And so you need to get rid of the fluctuations of the atmosphere. One way of doing that is to calibrate. So you measure a shear and you want to relate it to a true measurement. There is a direct relationship which involves a multiplicative bias. And the idea is to identify what this bias is. The approach is rather straightforward. It's like a poor man's version of the pipeline that particle physicists use to calculate Monte Carlo effects and stress test their experiments. This is, kids. It's like a child's toy compared to the sophisticated calculations that are done there. But in some sense, we're finding that we're almost being driven in that direction, that we literally have to do that. And we'll have to do that if we want to get to sub-percent level. But the basic idea is that you start with some mock galaxy distribution that has roughly the right number counts and the distribution as a function of distance, and has an appropriate ellipticity distribution for galaxies in the absence of lensing. You apply some known shear. You have an image that has been now distorted. You know what the shear is, so you know what the truth is. You calculate what the lensed image is. You add appropriate noise and distortions along the lines that you would expect in observations. You analyze the mock images. And presumably, you're using the same pipeline that you would use on real observations. And then you compare the output that you get to the true input that you had in the beginning, and you determine the multiplicative biases. It may surprise you at this point that The test that's been done to this up to relatively recently, about 2 years ago when we started doing this and discovered this effect, in doing the stress testing of the pipelines, in order to calibrate the pipeline, what was being done is that this is a distribution of galaxies as a function of magnitude. In other words, how faint they are. The fainter they are, there are more galaxies further away, but they're also smaller, more difficult to measure their sizes. And so usually there's a limit. At the 25th magnitude, you say the galaxies are too faint. I'm not going to be able to measure their shape. That's it. This is the faintest galaxies I will study. And then you go back and you calculate you make a mock image. And what was normally done is that the mock images literally only included galaxies up to the 25th magnitude. In other words, galaxies that you were going to use in your measurement. The fainter galaxies that exist in the real universe were just simply left out. And it turned out that when you do this, yeah, actually, this image is the right image. When you do this, sure, you get shearing. You can measure the shear. You can measure the shapes. You can determine the shear. It turns out that there is that you calculate a multiplicative bias, but it's not actually very reliable because these faint galaxies that's included in this image then starts to affect the images of the galaxies themselves. You have superposition of very faint but large number of background galaxies that is essentially creating a non-Gaussian noise in the image. And unless you can model that non-Gaussian noise and actually identify what the impact of that non-Gaussian noise is on the shapes of the galaxies you're interested in, you're going to mess up. And so we just started this as when we first started doing the pipeline and looking at this, this was the standard thing, was to stop right here, and that's it. And so when Hank and I were sitting around the table trying to figure out, what we had done and how to interpret the results, and we had a nice multiplicative bias measurement, it just sort of came out. What if we just went, included some fainter galaxies and find out what happened? And sure enough, it made a huge difference. And huge meaning it changed our mass estimates by 27%. So this is just a plot that shows this is the multiplicative bias. If you stop and only include the 25th magnitude objects in your mock images and then do the pipeline analysis, you get a multiplicative bias of up here. But if you then go ahead and allow for faint galaxies, then the multiplicative bias actually grows in magnitude until it saturates at some point where you have so many galaxies that you're starting to, yeah. No, but what happens is faint unresolved galaxy does two things. So first, if you think about a galaxy that you're interested in, it has contours to it, right? You're only measuring its shape up to certain faintness level. If you put an underlying galaxy that's not resolved, it actually brightens up a part of the galaxy and changes the shape that you will measure of the source galaxy. Then, if you have something that is sort of marginally resolved, it will look like it's blending with the source galaxy that you're doing, and that too changes the shape. And so you're completely missing out on the actual shape of the galaxy that you're interested in. And that introduces a huge error. So once you mess up on the shape measurement, then the shape measurement errors will transfer over to the shear measurements, and the shear measurements into the gravitational potential measurements, and so on and so forth. So it ripples all the way down the pipeline.
So is the multiplicative bias to correct the fact that, are we using the KSP algorithm?
Yeah.
Is that to correct the fact that it underestimates shear once you correct it? Is that what that's for?
Basically, yes. Yeah, yeah. So the issue here is that how much are you underestimating? And it turns out if you don't put the background galaxies, and then you want to do this, when you use that multiplicative bias on the real images, you actually are underestimating the underestimate. You need to increase your multiplicative bias. Okay? And so, as I mentioned, when you go through this process, the changes in the mass are at the level of 27%. Okay, so we can then go ahead and turn it into a mass measurement. But we only have 50 clusters. We can't really do cosmology. And so what we did was we took the Planck cluster catalog. So the Planck cluster catalog is, as I mentioned, Planck satellite went up, was supposed to measure the microwave background. But as a side benefit of that, it also measured clusters. It detected clusters using the inverse Compton effect. So in a nutshell, if you have photons from the microwave background coming at you, if you detect them completely untouched, then you see a perfect black body at roughly 3 degrees Kelvin. If the photons are passing through clusters of galaxies where there is hot gas at about 10 million degrees Kelvin, then the photons, some of the photons will interact with the electrons, and you will have a depletion in the Rayleigh Jeans part of the spectrum. So if you measure the black body the microwave background spectrum, you see a depletion of photons in the Rayleigh Jeans part of the spectrum. That delta T is directly related to the temperature of the cluster and so on and so forth. So it's an observable. And you can therefore detect clusters. The game really is to take a mass measurement, relate it to an observable, and basically come up with some relationship that you can then use more generally. Now, you could ask, why can't you go out and do weak lensing experiments on 10,000 clusters? Well, it's a very expensive proposition until these guys, Euclid and LSST, come online, after which they will clean up. But at this point in time,
even then, there's a limit to how accurate you can get the mass for an individual cluster.
yes.
And the observable can be much more accurate.
It could be, yeah, that's right, yeah. But in principle, at least, the selling point of LSST was to bypass the observable. But at least right now, we have a Planck cluster catalog that has 1,000 clusters. And the question was, can we use our 50 clusters to calibrate the observable from the Planck catalog and figure out the mass? So then all we have to do is go to the Planck catalog, pick up their Compton Y parameter for the individual clusters, map it to mass, and away we go. And so that was a game to basically deal with the Sunyaev-Zeldovich effect, which is essentially what I've been describing. I'm not going to go through this. I just finished describing it, but that's the effect. If you're interested, in seeing it visually, the spectrum changes largely because the black body photons in the Rayleigh Jean spectrum are being kicked up by the hot electrons, and you can detect this. So once you have that, you can go ahead and relate it with the mass measurements that we have, and that's what you end up with. So these, for the 50 clusters that we have, we can take the Planck Compton Y parameter, we can take our weak lensing mass estimates, we can figure out what the relationship between the two is, and it's given there if you're interested, and then essentially go back and calculate the mass for the 1,000 clusters that Planck sees and do cosmology. Look at the evolution. This thing seems to have moved. Yeah, okay. I'll start. I will just simply go to there. And what we have here are results from the microwave background experiments, which are sitting up here. And we have experiments from the cluster cosmology that's sitting up here. Now, looking at the plot in separate variables like this, it looks like it's about 2.5 sigma, maybe 3 sigma difference. And you'd say, oh, what's the big deal? It turns out that it is a big deal, because if you convert it into the number of clusters that you ought to be seeing in the universe, that's the result that you would get had you used the parameters that are derived from the microwave background. And this red points are the observed number counts of clusters as you see them in Planck. So Planck cluster and Planck CMB are in tension with each other. And the tension in terms of the number of clusters is at a factor of 2. There are factors of 2 fewer clusters in the universe than what you would predict had you used the microwave background results for the cosmology. And that illustrates, this plot sort of emphasizes this point in a slightly different way. For the kinds of calculations that we're doing with clusters of galaxies, the parameters of interest is the amplitude of the initial fluctuations on a specific scale that is standard in cosmology, and the density of matter to the power 0.3. The points here are along the red line, the black, the purple, the blue. These are points that are measured using large-scale structure. They're usually measured, most of them are done using clusters of galaxies. This is clusters of galaxies using X-rays. These two are using clusters of galaxies using ground-based Zeldovich-Sunyaev experiments. So is the SPT here. This is the red curve here. The red point here, down here, is the result you get from Planck if you used clusters of galaxies. And that's the result that you get if you used the CMB result. And that's discrepant. This is WMAP, which is the other CMB experiment, and it has a value that's lower and error bars that are larger. And so the WMAP people claim they're in agreement with the large-scale structure, and the Planck people would claim that they're in agreement with WMAP. The point is, there is a tension here. And so what's going on? There are a number of things you can worry about. Systematics in the Planck CMB data, or the WMAP CMB data for that matter. This, it turned out, was a problem in the sense that the Planck team had actually jumped the gun before they had completely kicked and shaken up their analysis. They had errors in it. It changed their numbers by a small amount, but not enough to do anything. One could argue that there are systematics in the Planck cluster analysis or even the Planck cluster catalog. I would argue that that's less likely because the ground-based inverse Compton measurements of clusters find similar results. X-rays, which are a completely different way of observing clusters, also give similar results. So there are multiple different ways that clusters have been studied, and they all seem to give the same result. And so unless the problem is with clusters of galaxies per se, this is not going to be a problem. And if it's with clusters of galaxies, then we're back to square one. We have to understand why. There could be systematics in our weak lensing analysis, and that is definitely a case. There is another collaboration that was working in parallel with us. It's called the Locus collaboration. They too find the same results as we do. And in fact, their results are much stronger because they have restricted themselves to clusters that are nearby and much better data. It could be that there is poorly understood cluster astrophysics, or it could be the failure of the vanilla 6 model, cosmological model that we've used, which could lead to new physics. And between these two, if I was giving a talk at the astronomy colloquium, as I will in a few weeks, I would have zoomed in on this one. And just for the benefit of this audience, I thought I would go with the first one, and I unfortunately do not have time to deal with both of them. So we'll go with this, and it's a very quick 2 slides, so I'm almost done. You can actually resolve the tension between the high redshift and the low redshift results. Remember, the microwave background is giving us results. If you take it at face value, then the microwave background is giving us a measure of the state of the universe at high redshift at 380,000 years after the Big Bang. The large-scale structure is giving us the state of the universe today. And so one way to address this problem is to introduce one extra sterile neutrino whose mass is somewhere between 0.3 and 0.6 eV. And that essentially moves a lot of the curves over. What basically is happening is that the neutrinos are relativistic. They count as the total matter distribution, total matter density at the early universe, but they do not aggregate as easily under gravitational attraction. And so they tend to smear out the structure. the amplitude of structure is lower, clusters form much later, not much later, but a little later, but enough to account for the factor of 2 difference. And that's certainly one model that, that can explain the tension. It can certainly resolve the tension. The alternative, which seems to be able to do exactly the same thing, is if you do not introduce a sterile neutrino, but instead of taking the sum of the 3 neutrinos that we have at 0.06, you have the sum to be, again, in the same mass range. So basically, you need neutrinos that have masses between 0.3 and 0.6. Does exactly the same thing. And the effects, the curves, if you compare the curves from the previous plot to the present one, it solves the problem in exactly the same way. And in this case, the tension, again, gets resolved.
So wouldn't this be in contradiction with the latest cosmological limits of the sound masses, which are around half an electron volt?
Half an electron volt?
Yeah.
Well,
They improve by order of magnitude.
right, so half would basically sit in there.
That was 95% confidence level. Like half by 0.4.
Right, so as that limit gets pushed down, these models will probably get, have to be tossed aside for something else.
These models also have cosmological assumptions, so I was wondering if, I think main input is from their acoustic oscillations.
Right.
It might be common systematic.
Yeah, so certainly the BAO measurements and the cluster measurements are consistent with each other at the moment. And so there is, but yeah, so yeah, so as their data gets improved and their limits become more stringent, certainly this class of model will start to get eliminated. But there are other variations. There are other models. So just yesterday on the archive, a paper came up, again mentioning this discrepancy. And there they had done a larger set of extended cosmological models. And they favored an evolving cosmological constant with a change in time. So something that would go down to have a value of something like minus 1.2 as you're going back in time. And that also it does exactly the same thing. It increases the acceleration of the universe and suppresses structure formation and reduces the number of clusters. So there are many variants, even within the area of physics, in terms of the nature of dark energy, in terms of possible extra neutrinos. The advantage of the extra neutrinos is that we see problems in the smallest galaxies. The very smallest galaxies have structures that are not quite consistent with cold dark matter, and a little bit of warm dark matter would certainly go a long way towards solving that problem. So anyways, I think I'll stop there. Thank you.
I noticed you've added an extra C to your.
Yeah, well, we joined forces with University of Washington, so we had to go with Cascadia and Cape Town. So collaboration grows, name changes.
Let me ask if there are questions. Please
Yes.
speak loudly.
So if you go back to your calibration, Y versus gather gas, yes, this one. So you use this linear regression, but it's a bit questionable, right? Because it's not clear that it will be correlated linearly. Have you tried some other kits?
We haven't, the locus people did, and there certainly seems to be a break at, not so much in mass, but in redshift. So the other thing I didn't mention here is that we have assumed that this correlation is independent of epoch, but it's not. And that that would be the astrophysics problem, that we have done it at in local universe. We have no idea whether this would hold even at redshifts of 0.5. Locus selected their clusters such that they only looked at systems less than 0.3. They found, so just to give you an idea of how things stood, I should go forward. Yeah, so there. So the black dashed lines there is a microwave background. The blue lines would be the result of our model, and the Planck people had assumed similar model. We just, in a way, confirmed that their assumptions were not unreasonable. The violet region is what Locus finds. So they have actually moved away from concordance. Their attention is higher when you use their results. So when we compared, I'm on that collaboration too, so and my first reaction was, we got to understand the differences. And it turns out it was as simple as, if you take our CCCP data and simply ignore all clusters greater than redshift 0.3, of which there are 5 or 7, we get exactly the same results that Locus does, which immediately tells you that this calibration is a function of redshift. And that could very well be a large problem in this game.
One of the big science programs for LSST in the 5 years before sort of begin to look at this at much more detail. This we'll be relying on. Well, we measure things directly through cleansing, but we are, the first order, relying on figuring out how the mass observable relations work as a test. There was another question.
Hi. So the discrepancies between high redshift measurements and low redshift measurements, so which are the local measurements.
Yeah.
So schematically, if I have to understand, so essentially there's either a problem with the local, like understanding of the astrophysics at say low redshifts, or say I can probably create a new particle physics model which between the high redshifts and low redshifts, which can sort of bridge the gap. But like if I have to schematically understand why there's a difference, is there something that
Yeah, so the way to understand the difference using the neutrino example as a foil is that you have a certain level of fluctuation. So you have an amplitude of fluctuations at high redshift. You have a universe that's expanding in a given way. It's matter dominated at an earlier epoch because the dark energy really hasn't kicked in until relatively recently, right? In addition to that, the CMB is basically reflecting the total matter contribution. So neutrinos, dark matter, everything counts in that calculation. But when it comes to structure formation, only dark matter, cold dark matter works. And so the more I transfer mass over to the neutrinos, the weaker I make structure formation, and I can delay it then. So think about it, it's an amplitude problem, right? If I start with a certain amplitude of cold dark matter, it will form structure earlier. But if I can take the total amount of matter at this epoch, but change it so that my cold dark matter is lower and compensate the rest by something else like neutrinos, this being lower means structure will form further down the line, which means today there would be fewer. Tomorrow, of course, there'll be more clusters, but certainly today we could account for the factor 2 less.
and of course the neutrinos are a minimal model. I mean, you
Yes, yes.
exotic where there's interaction between the dark matter and the radiation.
Absolutely. In fact, we were talking earlier this morning with Gigi, right? Yes. On things just of this ilk. Yeah, absolutely.
Can you say anything about the distribution, difference in distribution between dark matter and visible matter?
The difference is in, you mean in terms of the total, how much it contributes to the total mass energy?
It's interactive dark matter.
Oh, the interaction and this, no, actually not very much, because as far as astrophysics is concerned, there is scant evidence for interactions between dark matter itself as well as with dark matter and ordinary matter, except through gravity. There are hints. Part of the outcome of this exercise of analyzing clusters of galaxies was the we found 2 clusters, of which one the result was quite prominent. We found that these are merging clusters, so you have these large distributions of dark matter, gas, and galaxies colliding into each other. They look like a train wreck. Now, conventional wisdom would say that dark matter having very little or no interaction cross-section would basically pass through. Gas would collide and shock. And galaxies, being so widely separated from each other, might as well be treated as collision-less particles, would also pass through. What we found was that galaxies, sure enough, passed through. That was that image I pointed out where galaxies were at the 2 ends. The gas, sure enough, shocks in the between. We actually see the X-ray data, and we can see the shocks. What blew us away was, and maybe I can even show it to you. Yeah. So this is the image in optical. of that particular cluster that I'm describing. And this is the dark matter distribution. And again, if I flip it back and forth like that, you can see, right? So, okay, right here, there are no galaxies here. And yet there is dark matter. The only way you can get dark matter in this sense is if it has a sticky property, if it's interacting. So as it's coming through, there's some collision cross-section where there is a concentration of dark matter building up.
But isn't the picture of bullet clusters?
This is the anti-bullet.
Right. So how can you reconcile?
Velocity dependence of the interaction cross-section. Yeah. The problem with the cross-section argument is, at least when I talk to my colleagues in my department, I guess they're a little bit more conservative. The problem is we can calculate, we can estimate what the cross-section should be. It turns out, so I gather that in the standard calculation, the annihilation cross-section and the interaction cross-section would be related to each other. And the predicted annihilation cross-section would be too high. But a creative particle physicist ought to construct to be able to construct a model that suppresses that. But the point is that there are now several clusters that show this effect. This is one of the dark secrets of astrophysics that nobody wants to speak about yet.
Can you measure the velocities of this?
Yes, we can measure the velocities, yeah. In fact, we can, in this particular cluster, we can even measure the transverse velocities using Zildovich-Sunyaev along with the optical data, yeah. Yeah.
You can also measure it from the shock, like X-ray.
Yeah, from the X-ray shock too. That gives us one more constraint. So this is actually a system of 3 clusters colliding together, which when we first saw it, we labeled it as train wreck cluster.
This is an area where there are several groups working on trying to figure out how big this effect is.
Yeah.
It's basically a question of getting a large enough sample.
Yeah, the orthodox answer is that this should never have happened. But nature often doesn't really care what we think it ought to be doing.